yes, well, there are a few that we have made. These, on the whole, the ones that we have made are not homo-elemental, they're hetero-elemental. So some of the combinations of two different metals can be a little bit more robust often than if you have two of the same metal. But yeah, we have made a few that will hang around on the bench for a little while. But mostly because they're quite toxic, we don't really want to leave them so people can be exposed to them for too long. But yes. Well, so they're sort of proportionally related, but you're sort of getting onto quite an interesting question because eventually, because as our electrons gain mass, a lot of the ones that are really close to the nucleus get much closer to the nucleus, and eventually they're going to get so close that that the atoms can no longer exist because the electrons are crashing into the nucleus. So there's predictions of how heavy we've currently been making atoms, essentially. All of these ones down at the bottom of the periodic table, these don't exist even anywhere in the universe, maybe in the supernova of stars. And we're basically trying to make heavier and heavier atoms, but there'll be a point at which our inner electrons are so heavy and get so close to the nucleus that we cannot make heavier atoms anymore. So there's kind of a limit to how large we can make an atom. But, yeah. AR is what chemists typically use to denote an arbitrary aryl group. So these kind of six-membered carbon rings that you see here, so these skeletal formula, these are all six rings of six carbon, and we will use AR as a kind of notation for one of those rings. So that is those aren't argon atoms; they are aryl groups. So yeah, so these examples at the top. These are transition metal bonds, and actually, it's really actually much more straightforward to make transition metal homo-elemental bonds because typically the electronic orbitals of transition metals overlap with one another very effectively to make a chemical bond of some sort. When we get right down to the bottom of the periodic table, the electron clouds surrounding the atoms are so spread out, they don't overlap very effectively, so they tend to actually be quite weak. The bonding of actinides in general is quite weak, certainly in comparison to the transition metals. So I think that kind of answers your question. They tend to be weaker in terms of actinide bonds tend to be weaker and less stable.